Welcome to part 2 of the solubility product constant. Specifically in this tutorial, we're going to look at the common ion effect and solubility in pH. Factors that affect solubility. Two factors that affect the solubility of ionic compounds are the presence of common ions and the pH of the solution. So let's look first at the common ion effect. The solubility of a slightly soluble salt will decrease by the presence of a second solute that provides a common ion. Let's look at an example of how a common ion can affect solubility. The value for KSP for manganese 2 hydroxide, MnOH2, is 1.6 times 10 to the negative 13. Calculate the molar solubility of MnOH2 in a solution that contains 0.02 molar NaOH. So our strong electrolyte in this solution is our strong base, NaOH. And if I was to write an equation to show how sodium hydroxide breaks down, I'd say NaOH, a single arrow because I know this is going to dissociate completely, forming Na plus 1 and OH minus 1. And this would start out as a solid, and these would be ions in an aqueous solution. To write the dissolution equation for the manganese 2 hydroxide, I would write MnOH2 double arrow because I know, based on the given KSP, that this is not going to dissolve all that much. But it will dissolve to some extent. So I'm going to write Mn plus 2 plus 2OH minus 1. Then I'm going to take this dissolution equation and I'm going to put it into my reaction right up here. So MnOH2 Mn plus 2 and 2OH minus 1. And I'm just bringing the 2 from here down to here to remind me that that 2 exists in my dissolution equation. Now remember, manganese 2 hydroxide is in the solid state, so we're not going to have any values for this. And at the very beginning, based on this reaction, our concentration of manganese ions will be 0. Now, here's the difference between what we've done previously and what we're doing now. They tell us that they've added a strong electrolyte, and that strong electrolyte is sodium hydroxide. Now, we really don't care about the sodium because that's just a spectator ion. It's the hydroxide ion right here that is going to be the common ion between this equation and this one. So they are common ions to each other, so they're both going to be present in solution. So when I look at my initial concentration of hydroxide ion, if it was just this dissolution equation, it'd be 0. But because we've added sodium hydroxide to the solution, really, I have 0.02 molar NaOH. So my initial concentration will be 0.02 molar hydroxide because of this strong electrolyte. Then for the change, we're going to do what we normally do. Well, initially I don't have any manganese ions, but I'm going to get some over time. And then I'm going to have my initial concentration of hydroxide plus, and then I have to remember that this 2 is here, so this is going to be 2x. So I'm going to add some amount of additional hydroxide ions to the already existing 0.02. Now here's an interesting situation. The amount of hydroxide ions actually contributed, I should say, from this MnOH2 is going to be extremely minimal, especially when you look at the KSP value. So one of the things that we're going to be able to do based on this KSP value is disregard this value right here. Disregard. And again, that's due to this initial value of KSP. So now what I'm going to do is I'm going to write my KSP expression based off of this dissolution equation. So KSP will equal my concentration of my manganese ion times the concentration of my hydroxide ion and then of course we know that is squared. And then I'm going to go in and I'm going to substitute the KSP that was given to me for manganese hydroxide, 1.6 times 10 to the negative 13, very small number. The Mn plus 2 is going to be represented as Nx, and the hydroxide ion is only going to be represented by that concentration of hydroxide that was added in from the sodium hydroxide, and we're going to have that squared. So when I work this out, so when I solve for X here, which is really just going to be the concentration of my manganese ions, I see that that is going to be 4 times 10 to the negative 10 molarity. So that is the concentration of my manganese ions with this common ion added. So the next question that we should ask ourselves is, well, what's the difference between this concentration in the presence of this common ion if it wasn't present? What would my concentration of Mn plus 2 be if this common ion was not there? Would it be more soluble? Would it be less soluble? Let's take a look at that. So what would the original X be if the common ion was not added? So again, we're still going to have MnOH2. We're going to have Mn plus 2 and hydroxide. And we know that this is all gone. I should throw my 2 up here. Initially, if there was no common ion, this would be 0 and this would be 0. And then this would be plus X and this would be plus 2X. And then I'd write my KSP expression, which would be Mn plus 2 times hydroxide ion concentration squared. And then I'd take my original values, my original KSP, 1.6 times 10 to the negative 13. And I'd say the Mn plus 2 is being represented by this X. And since we're not putting the common ion in, this would just be 2x as it's coming from right here, but it would still be squared. And then this would be 1.6 times 10 to the negative 13, and that would equal 4x cubed. And then if we solved for this, we'd find that our x, which is going to equal our concentration of our manganese ions, would be 3.4 times 10 to the negative 5 molarity. So this is much more soluble. It's a much higher number, much higher number here for the amount of manganese ions that would dissolve in solution if that common ion was not there, if that sodium hydroxide had not been added. So the presence of a common ion in solution will definitely lower the concentration of any other ions that are in solution. And this is an application of Le Chatelier's principle. Now let's talk about solubility and pH. The solubility of almost any ionic compound is affected if the solution is made sufficiently acidic or basic. The effects are most noticeable when one or both of the ions involved are at least moderately acidic or basic. Here's the general rule. The solubility of slightly soluble salts containing basic ions increases as the hydrogen ion concentration increases. In other words, as the pH is lowered. The more basic the ion, the more solubility is influenced by pH. So some common basic ions that are influenced by increased hydrogen ion concentration will be something like your carbonate ion, your phosphate ion, your cyanide, sulfide, hydroxide, or fluoride ions. These are all considered weak bases. So let's look at an example. Consider MgOH2. My equilibrium expression is going to be MgOH2, reversible reaction with a partial dissolution into magnesium ions and hydroxide ions. The KSP value associated with this is 2.06 times 10 to the negative 13. And the calculated pH at this saturation is 10.52. what would happen to the concentration of magnesium ions and hydroxide ions if the pH of the solution was reduced to a pH of 9. So let's start out by looking at the magnesium ion concentration at a pH of 10.52. If I do 14 minus 10.52, I find that my pOH is going to be 3.48. So that equals my pOH. Then I know to find the hydroxide ion concentration, I'm going to take the antilog of my negative pOH. And if I do that, I find that my hydroxide ion concentration is going to equal 3.31 times 10 to the negative 4 molar. That's a 4 up there. All right, so that's my hydroxide ion concentration. Then I'm going to take my KSP expression. So KSP is equal to my magnesium ion concentration times my hydroxide ion concentration squared. I'm given a KSP, which is 2.06 times 10 to the negative 13. I'm solving for my magnesium ion concentration, Mg plus 2, and I have a hydroxide ion concentration, which is 3.31 times 10 to the negative 4 molar squared. So if I solve for my magnesium ion concentration, I find that that is 1.88 times 10 to the negative 6 molar. So in other words, the magnesium hydroxide here is going to dissolve in the solution until the magnesium ion concentration, there's a 2 right there, equals 1.88 times 10 to the negative 6 molar, and then we consider it at equilibrium at the pH of 10.52. So now the question is, well, what happens if you lower the pH to, let's say, a pH of 9? So now we have a pH of 9. pH equals 9, which means that my pOH is going to be equal to 5. And then again, I know that to find the hydroxide ion concentration, I'm going to take the antilog of my negative pOH. So hydroxide ion concentration is going to equal antilog of negative 5. And if I work that out, hydroxide ion concentration is going to equal 1 times 10 to the negative 5. Now I have my KSP expression. So KSP is equal to Mg plus 2 and OH minus 1 squared. I'm going to take my original KSP that was given to me, 2.06 times 10 to the negative 13, and I'm going to solve for my magnesium ion concentration. I have my hydroxide ion concentration right here, which is 1 times 10 to the negative 5 squared. And if I work this out, I calculate that my magnesium ion concentration, 2.06 times 10 to the negative 3 molar. So what does this tell me? It tells me that in a pH that equals 9, my magnesium ion concentration is 2.06 times 10 to the negative 3 molar. And at my original pH of 10.52, my magnesium ion concentration was calculated to be 1.88 times 10 to the negative 6 molar. So when I compare these two, I find that as the pH decreases, as it becomes more acidic, the solubility of my magnesium ion is much higher than a higher pH. Now, why is this? Well, the more hydrogen ions in solution, the more hydroxide ions that I need to neutralize that excess hydrogen ions, so more, in this case, magnesium hydroxide, is needed to dissociate to neutralize that excess hydrogen ions. And that concludes our conversation about solubility and pH.